Sir, good morning, sir.
Good morning. Good morning.
Good morning, sir. This is Dr. J. Diliban, sir, HOD MCA and Vice Principal Administration, sir. Thank you, sir. Thank you for joining and accepting our invitation.
My pleasure.
Thank you, sir. Thank you, sir. So within 5 minutes, we will start the session, sir.
No issues. No issues.
Okay, sir. Thank you, sir. Thank you. Sir, shall we start, sir?
Sure, sure.
Okay, sir. Madam?
Yes, sir.
Okay, madam.
Happy morning to one and all present here. On behalf of the SRM IST Ramapuram campus, we welcome you all for this day 2 session, 2-week International Virtual Professional Development Program on Data Science, a revelation of modern digital era, associated with CSI Chennai chapter, organized by the Department of Computer Application. And I extend my warmest welcome to our today's chief guest, Dr. Ayapputti Ayyappan Ganapathy, postdoctoral fellow, Khalifa University. Let us behind our session, pillar of the department, a very good planner, a man behind the success of every activity in our department, Dr. Dileepan sir, head of the department, Vice Principal Admin, College of Science and Humanities, SRM, IST to welcome the gathering.
Thank you, madam. A very warm good morning to one and all present here. I am very happy to welcome you to all to the day 2 of this 2 weeks online International Professional Development Program on Data Science, a revolution of the modern digital era, organized by the MCA Department, SRM, IC Ramapuram campus, in association with CSI Chennai chapter. First, I would like to extend my hearty welcome to our chief guest, Dr. Ayapputti Ayyappan Ganapathy, postdoctoral fellow, Khalifa University, UAE, with deep appreciation for accepting our invitation in spite of his busy schedule. It gives me immense pleasure to welcome all the participants from various institutions, even coordinators and faculty members. The topic of today's session is intuitively understanding variational autoencoders in deep learning. In the recent years, the deep learning-based generative models have gained more and more interest due to some amazing improvements in the field. Relying on huge amount of data, well-designed networks, architectures, and smart training techniques, deep generative models have shown us incredible ability to produce highly realistic pieces of content of various kinds, such as images, sounds, and text. So based on this, 2 generative models are very famous. The generative adversarial networks, GAN, and variational autoencoders, VAE. So it is an innovative and very interesting topic. So from this session, you can be able to understand about what is encoder, latent space, and how to generate the new data from the VAE and more. So I hope today's topics will be an eye-opening session for you all. So once again, I welcome you all to this wonderful session. Thank you.
Thank you, sir. Thank you for your warmest welcome. May I now invite Ms. Indumati, Assistant Professor, Department of MCA, to introduce our today's chief guest, Dr. Ayapputti Ayyappan Ganapathy, postdoctoral fellow, Khalifa University.
Good morning to one and all gathering here. I deem it honor and privilege in introducing for guest Ayapputti Ayyappan Ganapathy is now a postdoctoral fellow at Khalifa University, Abu Dhabi, UAE, where he is focusing on texture classification on 3D surfaces, image forgery detection and localization, as well as flare detection for effective smooth stack combustion. He has previously served as an assistant professor at Wuzong University, South Korea. He received a PhD from Indian Institute of Technology, Indore. During his doctoral studies, he researched in the domain of 2D and 3D computer vision to recognize humans using 2D and 3D ears. His research interests include 3D image processing, biometrics, computer vision, and machine learning. We are extremely happy to have such an eminent personality amid with us today. Thank you, sir, for accepting our invite and gracious this occasion. Sir, I invite you to take over the session, sir, please.
Thank you very much. for a nice introduction, and thank you for inviting me. So let us get into our business. Let me share the screen. Yes. I hope that screen is visible, right?
Yes, sir.
So I think I don't want to introduce again myself, like they have given a nice introduction. Let us get into the topic. Topic is generative models, and we will see something variational autoencoder. So the idea is, let me first tell you like what is the difference between discriminative models and generative models, and then it will be sort of more sort of like tutorial kind of session, and mostly I will try to cover the session like a story only. So if you have any doubt, you can ask, right? So let me get into, yes. So here is an introduction. There are two models, like one is discriminative and the other one is generative models. And whatever I'm giving in the bottom, it is the reference, right? So wherever I have taken the content, like many places, like even blog, books, and papers. So whatever it is I have given, that you can refer to the reference. The thing is like, what is discriminative model? It is some sort of neural network. Maybe I hope you all guys might aware of neural network. So what it does is like, we used to give training data, lot of training data, and we'll try to train this model. And once it is trained, then we will give some test images, and we will check whether the system is working right or wrong, right? So the idea is like, for example, we'll collect a lot of cat images. Actually, the task is to differentiate cat and dog. So we collect a lot of cat images, we'll collect a lot of dog images, we will give it as an input to this system. And what is this is neural network, right? So I will not get into that. Before to that, let us try to understand what is the model like as a layout. So once we give this as an input to the model, we'll train it. Then what happens is like, once the model is trained, when we give the test images, we try to classify it as a cat and as a dog, right? So this is discriminative models. And what is generative model? So the similar way, like suppose if I give like a lot of cat images as a training images to the model, and we train it, but here the idea is like, we will give some sort of random noise. And what exactly we want is like, we need to create some image like a cat, right? If I train this generative model for using dog, then what happens is like, if we give some sort of random noise, what we expect is like the output, it should generate some sort of dog image, right? So designing discriminative model is somewhat easy task, but it is not easy. At the same time, generative model is a little difficult as compared to discriminative model, right? So under this generative model, what we are going to see is a variational autoencoder, right? So the idea is like, generative model, if you train with lot of cat images, it will try to create a cat image which is not exactly same as the image what we have supplied while training, but the images what we got at the output, it will be different from the training images. At the same time, it will resemble the cat structure, right? So that is idea. So for example, let us take, we have a data generator, right? So this data generator generates some data, three-dimensional data. So here is one example, right? X, Y, Z, right? So it creates three-dimensional data. That means X, Y, Z. That means a point in 3D space. So let us take like it has created a bunch of points, something like this. We have a bunch of points, something like this. Now, if I ask you that if we would like to generate a new point, if you
சரியா இப்ப நானும் கிளாஸ் அட்டெண்ட் பண்ணோம் மறந்தே போயிட்டேன் கரெக்டா 10 மணிக்கு கிளாஸ் ஆன்லைன்ல ஒரு FTP மீட்டிங் இதெல்லாம் மார்க்ஸ் சரியா
no issues. If we would like to generate a new point, if you would like to generate a new point that would similar to this bunch of points, but at the same time that point should not be equal to any of these points, right? For example, so what we will do is, let me show you here. So for example, we can generate some point here, right? So there is, sorry, we can generate some point here, what I mentioned here, right? Somewhere here, and we can generate somewhere here, right? Somewhere here, but we should not put it somewhere over any of these data points. So the idea is like you are given with a bunch of points. We have to generate a new point that should not be similar to already existing point. At the same time, that should not be equal to already existing point. At the same time, it must be similar to these things. That means we cannot generate a point here. We cannot generate a point here because this is out of this cloud, right? This is out of this cloud. So now what we do is like, actually we don't know how this data generator generated these points, right? This data generated these points. There must be some underlying principle that this data generated might have generated these points, but how it has generated, we don't know. Now what we have in our hand is like bunch of points. Now what we'll try to do is like, using this bunch of points, we'll try to model something. So maybe it can be like a probabilistic model, right? So we'll try to model something out of using this bunch of points. So for example, if I show something like this, right? So what I'm telling is like, this is a distribution. Using this distribution, this data generator might have generated these points, right? So how did I say that? It is something like, you can find here like the middle points. You can find here the middle points. It is dense. That means here it is the peak one, right? Here the peak is at the center. So it shows that many points are at the center. And once we go away from the center, so what it shows is that the data is somewhat scattered. So what here is the highest value. And once we go somewhere away from this, so the peak is reducing, right? So peak is reducing. It shows that the points are somewhat scattered, right? So that's the idea. Now, why did I say this? We had a data generator, and this generator has generated some point clouds, and we don't know how this generated has generated this point cloud. So what we did is like using these points, we model something like this. We model something like this. Now, once we have this model, from this model, we can generate a new data. We can generate a new data. That's the idea, right? So let me show you here. Now, suppose you have a bunch of cat, right? So consider that these all bunch of cats are represented as points, right? Bunch of cats, it is represented as a point in a higher dimension, not 3-dimension, some are higher dimension, right? Some are higher dimension. So how it will be represented? The idea is like if you have 2 points, X and Y, so what you do, you can plot it somewhere in 2-dimension. If you have 3 points X, Y, Z, you can plot it in somewhere in 3-dimension. Now, if you consider this image, if you consider this cat image as somewhat like suppose 10 by 10 image, okay? So 10 by 10 image, that means it has some 100 pixel. I can represent this as some 100 pixels as a column vector, right? So meaning is like it is like 100 by 1, right? So what it shows, if you have 3 by 1, we represent this as a point in 3D space, right? I think I will. One minute, let me put a pointer so that this will be good. So the idea is like, yeah. So what I told you is like it, in 2D, X and Y, we used to represent as a point in 2-dimensional space. X, Y, Z, 3-dimension. This we represent it as a point in 3D space. Now, image, it has 100 dimension. Image, it has 100 dimension. As I told you, it is 10 by 10. So this 100 dimension, what will happen in a 100 dimension space, right? We don't know how it look like. So in a 100 dimension space, this each cat images can be look like a dot. These cat images can look like a dot, right? So the idea is like we have some data. From the data, we'll try to generate a model, right? So not generate, I can say estimate a model. Then from the model, we can generate the data. So that's the idea, right? So I will repeat these examples 2-3 times, right? So variation, once you understand these concepts, variational auto encoder, you can easily understand. I have only 5 slides at the end. Before to that, everything is basic only. Try to get the concept. So now, once again, I have taken a data generator. So now, in this case, it is not going to generate points. It tried to generate some images. Okay, so we don't know the underlying principle how the data generator is generating these images, but what we have in hand is like this type of images, right? So this generated some sort of images like this, but we don't know how this has generated these images. So like previously, what I told you is like from the bunch of points, we try to design or we try to estimate a model. From that model, we try to generate a new data point. Similarly, here what we try to do is like we have bunch of images. From these images, we'll try to estimate a model, and from the model, we will generate a new point. In this case, it will be a new image. For example, as I told you, like if each image, it is of size like 10 by 10, right? Each image of size 10 by 10. Okay. So I can represent it as a column vector, something like this, right? So its dimension is 100 by 1. Now in a 100 dimension space, so this each horse image, it will be as a point. It will be represented as a point. Okay. So here is the case. So each horse images, it is in a higher dimension. Actually, for visualization, I made it as 3, but actually it is a higher dimension. So in this higher dimension, so each horse image, it is like as a point, right? So now using this point, we try to estimate some model, right? We try to estimate some model. Now from that model, we can generate the data. So for example, I'm trying to generate a model, something like that, right? So what it shows is that if you have some data like this, if you have some data like this, like some dense points at the center and some scattered points at the end. Okay, some scattered points, some are like this. So what is this? I can draw a distribution, something like this. What it shows or what it says is that at the center there are many points. At the center there are many points. So here we are having the peak, and once we go away from this center, we are having the trailing edge. That means there is very scattered number of points, right? Very less number of points, right? So why I'm saying is that once from the data, if we could design something like this, now we can represent this distribution using two values. One is like we usually represented with mean, right? One we usually represented with mean. The other one is the variation, right? Variation or standard deviation, whatever it is, right? So if you represented it as a model, then using only two quantities, that is mu and sigma, we can represent this estimated model. Why I'm saying this? Once we know this mu and sigma, we can generate a new point. Like mu plus a sum epsilon. Okay, so this is some random number. Sample from another normal distribution. That means this bell shape, right? Somewhere I pick a number and I put it here, right? So it can be like a number that is maybe like 0.1, some random number. Okay, so once we know this mu and this standard deviation sigma, then we can generate a new data z, right? So this new data, in our previous example, it was a point, and this example, this new data, it is an image. This is an image, right? So repeatedly I'm telling, we will be having some data only. We don't know how this data has been generated. So what we try to do is like we try to estimate a model out of this data. And once we estimate the model, from the model we can generate a new data. So that's the idea. So let me show you. So this is what I told you. Now let us see something like what we design here. It is nothing but a probabilistic model, right? It is nothing but a probabilistic model. So the summaries in this slide. So what we try to do is here, we try to generate a horse image. So what we do here, we collect lot of horse image, right? So we collect lot of horse image, Now we have the data. Now we have the data. Now from this data, what we need to do is we need to estimate a model. We need to estimate a model. So estimate a model in the sense something like this, right? So it is not always like this. For example, I'm showing. So once we estimate the model, right, then we try to sample a point from here. Try to sample a point from here. Now this is going to be our generated data. This is going to be our generated data. So that's what here shown. So now how do we design this model, right? How do we design this model? Because it will be like somewhat a complex model. So this model, there we take the help of neural network. There we'll take the help of neural network, right? So because it is not deterministic, so we don't know how to generate the model. So we will be feeding a lot of images to the neural network, and it try to generate a new image. I mean, say it try to come up with a new model, right? It try to estimate a model out of the given data, and from that will generate a new sample. So that's the idea. So why I'm saying this like this, the reason is, suppose if you're having an image like this, consider it is 2 by 2, right? So this image has only 4 pixels. So this image has only 4 pixels, right? So if you want to generate an image, right? So how difficult it is, the reason is like, suppose each pixel takes maybe represented with 8 bits. Okay, each pixel represented with 8 bits. Okay, so that means it can take like 2 power 8, that is 256 different colors. I mean different shades, right? Each pixel can take 256 different shades. Now you think of, we need to generate these 4 pixels. We need to create, right? We need to create these 4 pixels, and each pixel can take 256 different shades. Now we need to come up with a new image like this. And in this place, if you have a horse, right? If you have a horse image, you see like here it is somewhat green, here it is somewhat brown, right? So each pixel should have some certain value such that after generating those all pixels together, it will represent it as a horse, right? So there comes the difficulty, right? So that's why we collect lot of images, and we'll give it as an input to the generative model. It try to estimate, and it try to learn something from those bunch of training data, and out of that we'll generate. Right? So that's the idea. Now, yes, let me tell you one more thing is, it is something like you may think like, why don't we generate something like this? The easiest way. Suppose I have some 100 horse images. Okay, so I have some 100 horse images. So every time if I want to generate a horse image, you may think that why don't we take some 10 horse images, and why don't we sum up all these and come up with a new image, right? Something like this. Take some horse images like this, right? Now this is the first pixel at each image. So if you sum up all this, you can come up with a new image, right? You can come up with a new image. May or may not this represent it as a horse, but the idea is like, if you do this, right? So one time if you sum up all and if you come up with a new image, it may or may not represent a horse. For example, let us consider it represents a horse, right? Now the idea is like, every time you sum up, and if you follow the procedure with some fixed calculation, it will give the same image. It will not give you a different image. But the concept of generative model is like, every time when we try to generate image or try to generate the data from the model, it will give new image, right? but here, if you do some sort of fixed calculation, it may not give a new image. It will give the images, the same image repeatedly. So that is one of the problem with going with some sort of fixed calculation, right? So this is, for example, I told you, like, summing up. You can like go for multiplication or some linear combination of these all images, right? So whatever you do, at the end of the day, you will get an image, and that image will repeat once again if you do the same calculation. So that's why. So again, as I told you, I will keep repeating the same concept only. So once you get the concept, then to understand variational autoencoder, it will be very easy. So what we discuss is, we have data set. Now from this, what I told you is, like, we will try to estimate a model. So once we estimate a model, we'll try to pick a sample, right? Try to pick a sample. So in the sense, like, it is not necessary like always like this. The distribution may be like a rectangle, right? So otherwise the distribution may be somewhat like this. So it is not necessary. For example, I'm trying it like a normal distribution. So the idea is, like, these images, as I told you, we will be having the images something like this. So out of this, we'll generate a model. Now once we estimate a model, once we estimate it, we can pick a new point, right? We can pick a new point. We can pick a new point, and what we expect is, since these all 5 points are hours, so somewhere in between, if I choose a point, we expect that this point may also resemble the horse image, right? So that is the main idea. And to assure or to ensure that these to happen, right? So here the space, it should be continuous. It should be continuous. So when I get into autoencoder, and then from autoencoder we will get into a variational autoencoder. That time, let me tell you. So let us pick a sample, and that sample is nothing but generated image. So yes, the idea is to find the unknown probability distribution. That's what I told you. We need to estimate a model, then we can generate a new model, right? So that model generate a new image. That image should be similar to the image in the data set, but it should not be exactly same as the image in the data, right? So let me show you another example. Once again, I'll take another example with a different distribution, so that you will get more idea. So now you have a bunch of points, something like this, right? So in the previous cases, what we had is, like, intentionally we had something like a bunch of points, something like this. So we have estimated a model, something like this, right? Now the idea is, like, we have somewhat scattered points, right? I cannot draw some model, something like this. So what can be the estimated model for these points, right? So let me first explain. So we have a data generated, right? So this data generator, it follows some distribution. It follows some distribution. For example, something like this, right? It follows some distribution. And from this distribution, it has generated this data, right? We actually don't know what is this distribution. Actually, we don't know what is this distribution, right? How it has generated this data, we don't know. Now, we have only these points in our hand, and from these points, we need to estimate a model, right? So how we can estimate a model? What type of model we can do? The easiest way is, like, how much these points at this side, it is up to this level, right? And down it is up to this level, and this side this level. So what I can do, I can put a rectangle box. I can show that this can be the distribution in the sense that, for example, it is like this. It would be like this, right? So we can put a box and we can say that from this box, right, these points are randomly picked. From this box, these points are randomly picked. We can say something like that, right? So in the previous case, when we were discussing, when the model is like this, what we try to estimate, the meaning of estimating the model means, like, we try to choose the point, like we try to find the parameters. One was mu, the other one was sigma, right? So for a distribution like this, the estimating means we try to find out these parameters, mu and sigma. Now the model is look like this. So what parameters we have to estimate here? It is like, if you want to draw a box, right? So if you want to draw a box, if I have 2 points, one is this point, the other one is the other point here, right? So if you have 2 points, then we can easily draw, right? So if it is x comma y, or x1 y1, and if it is x2 y2, right? If I have 2 points, then I can easily draw a box, rectangle box. So the idea is like, in this case, we try to estimate mu and sigma, and in this case, we try to estimate the parameters, that is x2 y2 and x1 y1. Why I'm saying this? The reason is, if you know these 2 numbers, we can draw this box. And as I told you, like, from this box, since we don't know what was the true distribution from the data has been generated, we don't know. That's why what we do is, like, from the given data, we try to somewhat come up with some conclusion, right? So there may be possible that the given data, these points, might have generated from this box, right? So that's the idea, right? So now, if suppose I ask you to generate a new sample, right? We got a model now, right? So the model is nothing but this box. Now, if I ask you to generate a new data, that means somewhat like this black dot. If I ask to generate a new data, what you can do, you can pick somewhere here, you can pick somewhere here, right? You can pick somewhere here, right? So what does that mean? Since this is our estimated model, now from this model, I can randomly pick, right? So in this case, if each point, if it represents some image, suppose some cat image, if this point represents some cat image, if I pick a point from here, what we expect, this would be also a cat. Right? But how this can be a cat and what type of difficulties are there, we will see. But the time being, that's the idea, right? And as I told you, let me show you another image. Yes. Here, what I told you, this unknown distribution, how this data generated, we don't know. So what we did is we estimated something like a box like here. But actually, the original distribution, let me show you here, how this data is generated. Let me show here. It is from the world map. Okay, it is from the world map where the land mass are present, right? So you see here, this is the background world map with the land mass. The idea is that this image actually generated from this distribution. The distribution, now it is a world map. Okay, so now I can choose a point here. I can choose a point here, and then I can say that yes, it is from the landmass. It is from the landmass. So I can say that this data can be similar to this bunch of points. The reason behind is I'm randomly sampling, otherwise randomly picking a point from this world map landmass. At the same time, if I choose a point somewhere here, it is out of world map landmass, right? So wherever the land present, there only this data has been picked, generated. So if I put a point somewhere in the sea, this cannot be a correct point. Otherwise, we can say that this cannot be a point that is similar to this data, right? So now with this concept, you see here, this B point, which is overlapping with already existing point, right? So what does that mean? We have a bunch of cat images. Now, we wanted to generate a new cat image. If this cat image looks similar to one of the cat image present in the training data, that means that is not generated data. Right? So the newly generated image, it should not look like equivalent to any of the image present in the training data, but it should look like a cat. Right? So the same thing, if I choose a point somewhere here out of this distribution, then this is a point. It is not similar to this bunch of points, right? So here this point is not valid because this is overlapping, right? This B cannot be a generative. At the same time, A, it is in the C, it cannot be once again generative because our distribution is the landmass, right? But you see, you can find this point C, it is in the landmass. At the same time, it is not overlapping with any of the already existing points, so it can be a generative uh, point, right? So this is how we generate data, right? So this cannot be generative and this is generative. So let us take an example now. I think now things may be somewhat clear. So here is an example. Okay, we have given with some bunch of data. So this is your training data. Consider this is your training data. Okay. Now from this data, you need to generate a new image. Right? So how we can generate that, right? So what I'm doing is, let us find first what are all different features there. For example, if you take hair color, right? If you take hair color, the hair color is, here it is black, here it is red, and here it is brown, right? And here it is somewhat silver color, right? So uh, there are different hair color, there are different cloth style, right? The top is like, here it is round neck, here it is V neck, right? The top is somewhat different style. So what we try to do is, like, we try to pick up those as the features, right? Let us try to pick up those as the features. So here is a case. So this is hairstyle. One is hairstyle. The other one is uh, the spectacle shape. This is sunglass, and this is round glass, and this guy does not have any glass, right? So this is accessories type. Now the third one is cloth type, as I told you, right? So it is round neck you are having here. It is somewhat different shape, and here it is V shape. So we are having different cloth type. Hair color, black, red, different colors. And here is again cloth color, like you can find white, I don't know what is this color, blue, red, something like this, pink. So we are having different colors, right? So now the idea is like, so this is an example, right? This is an example hairstyle. Idea is that using these all images, we want to create a new image. We try to go with a simple probabilistic approach, right? We try to go with a simple probabilistic approach. The thing is like, yeah, it is an example. It is an example, like long straight hair and red hairstyle, right? Hair color is red and the spectacle is round and the cloth type is round neck, scoop neck, and the cloth color is white, right? So where is those image? You can find those image. It is here, right? These two images similar to this one. These two images similar to this. Now, using this, how can we go with something like to generate a new model, right? So let me show you here. So here is a case. There are 7 different hairstyles, 6 different hair colors, 3 different kind of glasses, right? 4 different kind of clothing and 8 different kind of clothing colors. Now, yeah, 3 different kinds of glasses. That's what I told you. One is blank, another one is round, and the other one is sunglass, right? So now we have some features like this. Now, out of these features, what is the task is to create a new image that already not exist in the database or the given data, right? So the idea is like, I can choose no hair. I can choose no hair. Let me choose another color. I can choose no hair and I can choose black hair color. I can choose a round glass. I can choose overall maybe top, and then I can choose the cloth color as blue, right? So now all this together, I can generate one image. I can generate one image, and with the condition that this image should not already present in the data set. That's the idea. So now, if you go like this, how many different combinations are possible, right? How many different combinations are possible? Like here is 7, here is 6, 3, 4, and 8, right? So if you multiply all those, that many combinations are possible, right? So that many combinations. So we'll be having like somewhat around 4,032 combinations are possible. So what it shows is like, if I draw a distribution somewhat. So for example, I'm drawing, right? So we will be having like 4,032 points. We'll be having 4,032 points. So what's the idea is like the probability distribution, the sum of the area, somewhat it should be equal to 1. That was the basic, right? So now what we try to do is like, we try to estimate each point. What this each point represent, it is nothing but a combination. For example, this combination represent this point. That means straight hair, red color, hair color is red, and then round neck. No. This is spectacle is round, scoop neck and white. For example, it represent a point here. So 4,032 points are represented like this, and we try to estimate a model something like this, right? So what does that mean? There may be possible that some points may have these peak, some points may have peak, and some points may have less probability. Some points may have less probability. So let me show you again the data set. You just look at the data set and tell me which of those images could take these the highest peak, and which of those images take this less peak. That means with less probability, right? So let me show you again. Just look it out, right? Here, the most let us take hair color. Okay, hair color. This silver type of hair color, it is there are many, right? Compared to red hair color, compared to red hair color, the silver hair color, there are many. You see 1, 2, 3, 4, 5, 6. There are many. There are many silver hair colors. At the same time, you see the top, top in the sense, I mean to say, like the dress, right? The dress color, you see the white, there are many. White, there are many, right? As compared to pink, white, there are many images, right? So what we can expect is which one should take the peak. There is a possibility that if the combination that is with some silver hair, right? Somewhat with silver hair and white color cloth color, cloth color, it may take maybe a high probability, right? So the combination of these images may lie somewhere in the center, But what images may lie in the trailing edges? You can see again. It is like the rare images. For example, the pink dress, there are only 3 and 4. There are only 4, right? You can find the blue color cloth. There are only 4. So these all are rare. So what we can expect is those combination may lie in the trailing edge. That means it has less probability. And this combination, it may have the high probability. So here is one example. Long straight hair, red, round. That already shown you that these two, I've shown it as the combination. So how many total images are here? It is 50 images, right? There are 50 images. Out of 50, the combination what I've shown. Okay, this is the combination. Okay, this combination, out of 50, there are only 2 combinations. That means it must have less probability. So what is the probability? We'll be having 2 by 50. Right? So out of 50, we are having only 2 images that match this combination. Right? This combination, so it has only 2 by 50. So that's ideal. So now we are having 2 by 50. That's done. Now the problem is that here the reason why I am keeping like 431, because you have 10 values. Okay, if you want to estimate 10 values, as I told you, probability distribution, the sum should be equal to 1. So that means if you estimate the 9 values, then this one we don't want to estimate, because the sum should be equal to 1. If you know the 9 values, then the last one you can know it easily, right? So that's why it is out for 4032. We are estimating 4031. Right? Now the idea is like, if suppose in this place white, if I come up with some other combination like blue, right? So actually this combination is not present in the data set. This is not present in the data set, this combination. So what you will get, the parameter, you will get it as 0. That means we cannot generate a combination like this with the cloth color as blue, right? So it is one of the difficulty. If you go with somewhat a basic probabilistic model, right? So let us move to another model. That is naive Bayes, right? So what we consider here is like each features are independent. So why we consider each feature is independent? So that we can multiply the probabilities of each features, so that we can easily get the result, right? So all features are independent. How many features are there? There are 5 features, right? So there are how many features? There are 1, 2, 3, 4, 5. There are 5 features, right? So we have 5 features. So what we do is like, let us take, for example, the specs type, the spectacle, right? Let us take the spectacle. Spectacle, one is the person without spec, and the other one is with round spec, and the other one is sunglass. Total number of images is 50. So let us count how many are blank. 11. So 11 divided by 50, you will be getting this, right? So likewise, you can calculate all. As I told you, the sum that is equal to 1, right? That sum it is equal to 1. So what actually finding here, we are trying to find something like this. Find something like this, right? The peak one is like having 0.44. That means the round glass. The round glass has the maximum peak, and the blank has somewhat 0.22, and the sunglass has somewhat 0.34, right? So it is somewhat like this peak. So it should not, like, so it is something like this. We try to find the distribution like this. Anyhow, the similar way we can find for top type, cloth type, hair color, cloth color, for everything the similar way. We need to find, we need to count those for each features, and you need to estimate something like this. So what we have is, why we are doing this, because using naive Bayes, we will get something. In the previous case, with the blue combination, we got something 0, right? So in this case, we will get some value. It will not be equal to 0. That means we can generate something that was not present in the data set, right? So here is the case. We can calculate something like this. For top type, you calculate the parameters, the distribution, right? And here you can calculate the distribution, each of them, right? So we find like different distribution for each of them, right? So now we have 5 distribution. This is what we have seen in the last slide. Now, if we get the combination this one, what should be the value? What should be the value? You see here, for long hair straight, so you can find the value is this, right? For the red color, the value is this. And for round glass, the value is this. And for scoop neck, the value is this. And the blue one, the value is this. Now, if you multiply this all, this multiplication comes, that's the reason we consider that all the features are independent, right? So once we multiply, we will get a probability that is somewhat equal to 0.001, right? So in the previous case, it was 0, but in this case, it was not 0, right? That shows that it can create, I mean to say, a new image with a different combination, right? If you take any combination, we can generate the image. So you can find here. So these all are the generated image. Okay, these all are the generated image. What you can find here, what you can infer, it is like, as we have seen that there were many white color dress, right? In the given data set, there were many white colors. You can find here the newly generated data, most of them got white. The reason, our model, estimated model, where the peak was, I told you that with the silver combination hair and the white cloth type, it was having the peak, right? So the reason is, once we sample from this model, there is more chances that the point may pick from here, because this is the place where the dense points are there. This is the place where dense points are there, right? So that's why you can find many white clothing type is there. At the same time, you can find many silver hairs are there. Many silver hairs are there. And the rare cases, something like pink dress, there is only one, right? There is only one. And you can find here the rare color like a red color hair, it is only one. So this is what I mean to say. So how you provide the data, so likewise we can generate, right? So if you give all images as red color cloth type, then we cannot expect that the system will generate something of some different color, right? So that is called biasing, right? We should not bias, right? So we should train the system with proper data, then only we can expect the output can be generated somewhat like a new image, right? So if you give all of a white color cloth, we cannot expect the system to generate black color cloth, right? So we should provide the data, then only it will come. That is one example is this one, right? We have given many white dress, so the generated data is also white. Yeah, most of the samples generated have white hairs, right? Now naive Bayes also fail. Actually, when we come into the real scenario, this also fails. The reason is that the previously actually it was an image. It was an image, but we considered like hair, all the hairs as one feature, right? And the spectacle as one feature, right? So we have taken, I mean to say 5 features only. We have taken 5 features out of an image, right? 5 features out of an image. You know, actually, if you have an image, suppose it is 10 by 10 image, so we'll be having 100 pixels. We will be having 100 pixels. Now, what was the actual thing we have to do is like we need to decide each pixel, how it look like, right? So each pixel, whether it should be black color or blue color or red color, right? So we need to think of each pixels. So in that case, this naive Bayes will fail. The reason behind is, let us consider here each image, let us consider the size of 32 by 32. It is of size 32 by 32. So now total how many pixels will be there? It will be 1024 pixels. There will be 1024 pixels, right? So each pixel will take a combination. Suppose if it represented by 8-bit, it will take 256 different values. Each pixel will take 256 different values. So how many features? 1024. How many each pixels will take? It will take 256 different values. So like the previously, how I have shown you to calculate the distribution for each features. So here we are having like 1024 features. You can calculate for each features the distribution, right? Then if you multiply all these 1024 together, what you will get a value that shows that how the image will be, right? So here is the case. So we'll be having 1024 features, and each feature can take somewhat around 256 values, right? Using this, if we generate the image, actually it look like this. So the idea is that here we try to generate each pixel values. One thing you can notice here, like except this person, the remaining, the background, it is black, right? So you can find the same thing in the generated image. Yes, it works. It works because the background is black. That is okay. But the remaining thing, it is not as good as how the data present in the data set. The thing is like you can check pixel by pixel. It seems that all similar, but actually pixel by pixel it is different, right? Pixel by pixel you can find that most of the things are different, right? So this is one of the thing like naive Bayes will fail when you go with pixel by pixel. And another thing is like we considered that each features are independent, but in image like one pixel is here and the nearby another pixel. If it is green, most probably this may also be green, right? So there may not be like sudden changes, because if it changes suddenly, then it may not look like an image, right? So it will look like a noise only. So there may be a relation between one pixel with another pixel. But what we did is like we assume that the features are independent. So that may not work here, right? So it is another case. Yes, to overcome these all things, actually where we going is right now we are entering into variational autoencoder. So this is variational autoencoder. So what it does is that I think looking at this image, you may get some idea. You see, this mu and sigma, this is what we estimated, right? As I told you, we tried to estimate a model, right? So once we estimate a model, from this model, we can sample something. Then that sample, we expected that can be a cat or duck, right? This is what I told you in the beginning. Exactly that is the case of autoencoder. Now, how do we estimate this? It is done by one neural network. We call it as encoder, right? We call it as encoder. Now, from this space, we sample a point, right? For example, this is like what we call it as latent space. This what we call it as latent space. Is nothing but if I have an image, right? So if I try to represent this with a reduced dimension or with what to say, expanded dimension. So mostly we'll go with reduced dimension. For example, if it is 10 by 10, so it can be represented as a vector of 100 by 1, 100 by 1. And if I try to represent this as a 10 by 1 vector, a 10 by 1 vector, right? This is called the latent space. This is called the latent space, right? Some reduced dimension. If you might have studied, come across PCA, right? So how you reduce the dimension, a similar way. It is done using neural network, right? So that is latent space. So here is once, so the idea is like this image, it is reduced to a vector size of 10 by 1. Now this 10 by 1 is once again reconstructed back to the same size 100 by 1. So who is reconstructing? This guy is reconstructing. It is actually another neural network. It is actually another neural network. So the idea is like, here is a loss function. What is loss function is like, we actually wanted to reduce this. Actually, we wanted to reduce this. Once this loss function goes less, right? Then we will get a good image. Okay. So the thing is like, suppose if this is a cat image, if this is a cat image, actually what we want, right? And if this is the predicted image, otherwise if suppose this is the image generated, right? So consider this is the generated cat. This is the generated cat. The difference between this, if it is small, then the loss function will be small. That means we have generated a perfect cat, right? At the same time, there is another loss function. They call it a scale divergence. And let me tell you once we go into the other slide. Okay, otherwise I can tell you like, no, nothing. It is this n, it represents the normal distribution, that is the bell shape, right? So what we have is, we have a zero mean. This is mean, this is mean, and this is variance. Okay, so zero mean and the variance of 1. Zero mean and a variance of 1. And what we have is, this is something the neural network tried to come up with the estimated model. This is what, right? It is come up with some estimated model. If this mu, it is far away from 0, or if this variance, if it is far away from 1, then what it does is that it try to penalize. So penalize in the sense, this term will increase. So once it increase, the loss will increase. So actually what we wanted to do, we wanted to reduce the loss, then only we can generate a good sample, right? So this scale divergence, it is try to compare how similar two distributions are, right? So that's the purpose, right? So there are two distributions. Try to find out how similar these two are, right? So yeah, this is some I will explain you now. So for example, consider this guy is receiving some numbers like 0, 1 up to 9, right? But different zeros. Zeros can be like this, zeros can be like this, zeros can be like this. Like there are bunch of zeros, there are bunch of ones, right? So one can be like, and like there are different ones, and he is receiving all digits with multiple samples, right? He is receiving all digits with multiple samples. What he do is like, if he receive a digit, he try to map this digit to a two-dimensional space. That means if it is 7, he try to map it something like this. So if it is 0, he map something with some different number, right? So maybe like some 0.9 and some 1.5, right? So if it is once again 7, then he may map something near to this, because already mapped 7 with the point 0.2. So he may map something near to this, something like this, right? So likewise, he mapped all the points somewhat look like this. So what is this? Each point here actually represent a digit. Each point here actually represent a digit, right? So be clear. So each point is represented with two numbers, something X and Y, right? So a digit image, once he receive, he is reducing that image to two numbers, So that's why he's called as encoder, right? He's called as encoder. Now the problem with him is, yeah, actually, this is actually, I should say, is like autoencoder. Then we'll come to variational autoencoder, right? This is autoencoder. The problem here is that, yeah. So here all the digits are mapped to each point. As I told you, each point is nothing but a digit. So suppose this point is 6. So Mr. Encoder, he received 6 and he mapped to a two-dimensional space. And if you want to get back that image, so each point will pass through a decoder, and the decoder will reconstruct something like this. That's the idea. Now the problem here is that you can find there some sort of clusters, right? You can find some sort of clusters. Let me show you again here. You can find this image. There are some sort of clusters. Here is one color, and here is some one color. So what it shows is that this color shows 0, right? So these all points all together representing 0, and these all representing 1, right? And you can find if it is 9, this all red color, this represents 9, right? The thing is that there are equal number of samples for each digit. However, the thing what we get in the, mapped in the two-dimensional space, actually this is the latent space. Actually, this is the latent space. The two-dimensional space, how it is mapped, it is not actually equally distributed. One number taken like large space, the other one taken very small space, right? And the other thing is like it is not symmetrical. This all are the properties, this phase problems, right? So here it is not symmetrical. So these all things actually created problem with autoencoder. And once reconstructing the image, actually it is not clear. So what we get is something like this. As I told you, this 9 red color, you can find near to red. So it is reconstructed to 9, but it is not clear, right? The same one, this one is somewhere far away from this point cloud. Actually, it represents 1, and it is reconstructed it as 1. But still, the points are not clear. So what exactly we want to have is like, if each of this spread, each of these point spread, if it occupies the equal space, and if it is somewhat symmetrical with respect to 0, right? Then we expect that this may be the reconstruction will be somewhat good, right? So this is the reason I have told you there in the beginning that KL divergence loss, right? We will see that one again. Now we are coming back to variational autoencoder. Now what he do is like he receive an number. Actually, he encoding this to some 2-digit. He will map to 2D space. But this time, what he do is like he is employing another lady, right? So this lady will plot this number to the 2D space. Once he give this number to her, she get this number and she will plot somewhere near to this number if he is confident about this number, right? If he says that, yes, I'm very confident that 7 should be mapped to 0.2 and 0.4 in the two-dimensional space, then she can map this to somewhere near to 0.2, 0.4, but not exactly on 0.2, 0.4, right? And suppose if he is not confident enough, what she will do, she may point it somewhere else. If he give 0.2, 0.4, and if he says that I'm not confident that 7 can be mapped here, but anyhow, this is my number, so you map it somewhere else. So what she do is like she maps somewhere far away, somewhere like little far away, right? So another thing is like, excuse me, I have to take urgent call, 1 minute. Sorry for the disturbance. The thing is that he used to give it like with the confidence that this is the number, so you can plot it somewhere. Now the thing is like, if he give this point somewhere far away from this, I mean, she is standing here in a ladder, and if he give this point somewhere far away from this place here, he actually have to pay something to her as an additional payment, right? So what is this additional payment? That is nothing but that KL loss, right? So what we have seen there, right? So it should not go away. At the same time, he should be confident enough so that if I try to take this point, then I can reconstruct the point exactly, right? So this is the thing I have shown here. Yeah, this is the thing I have shown here. What it is does, if we are moving away from mean 0, that means the lady standing at the center. If it is moving away from the center, then this loss will increase. This loss will increase, right? And the the other thing is like that guy should be confident enough so that the reconstruction should be perfect and this error will be less, right? Now, this is the concept of autoencoder. This is the concept of variational autoencoder. The difference between autoencoder and variational autoencoder, it is something you can find here. This is the case. In autoencoder, actually we map it to a point in the latent space, right, as a point. But in case of variational autoencoder, it is mapped as a distribution, something like this, a normal distribution, right? So this is what does that mean? It is like this peak value represents 6. At the same time, if I take somewhere here, this also represents 6. This also represents 6. Since we are mapping somewhat like a distribution like this, what we confirm is that if I have a point here, the nearby point, this is also similar to this, right? So by saying this to the autoencoder, what we ensure is that the space is somewhat continuous, right? So this is the idea with variational autoencoder, right? So likewise, what I told you, like cars and other things, people generate faces. Like if they give like a face with a sadness, and that face can be reconstructed with a smiley face, right? There are many things, right? There are many things you can find with autoencoder. So this is the basic concept. Like if you have a data, right? So we'll estimate a model, and the model what we estimated here is like mu1 sigma, and from this model you can sample a point, and from that point you can generate a new new image. So this part, it is done by encoder, and from the sample to reconstruction, this part it is done by decoder. So that is variational autoencoder. This is the maybe story, right? So if you go through any one of the literature, you may find it. You can find it somewhat. If you want to go in depth, then I think this may be helpful for you, right? Thank you very much. Thank you very much for the opportunity.
Thank you, sir. Thank you for your informative session, sir. Sir, you gave a roadmap to train, test, and generate the data with the images, and you also tell the estimate how to estimate a higher dimensional data to generate the data with the images. Thank you, sir. Now I call upon Ms. Indumadi, Assistant Professor, Department of Computer Application, MCA, to deliver the vote of thanks.
It gives me an immense pleasure to deliver the vote of thanks for this event on behalf of the management of SRM IST, Dean VP Academic and VP Admin. I thank to everyone to give the nice session. First, I would like to thank management of SRM, and I would like to thank head of the department to permission to conduct this event in successful manner. I would like to thank the conveners, Dr. Uma Shankari ma'am and Ms. Indumadi, to organizing this 2 weeks international FTP. I would like to thank our department staff members for supporting to us to successful this event. I would like to thank today's chief guest, Dr. Ayakuti Ayappan Ganapati, who honored this PDP session on day 2 with his valuable inputs in variational encoders. Sir, it's very useful for faculties and research scholars. Through the sessions, we learned generative deep learning methods, autoencoder concepts, how to generate the model by the way of generating modelings, and you have stated the topic of the image generations with the examples of Audience, please mute yourselves. Audience, please mute yourselves.
TST எங்கடா இருக்குது?
Sir, you explained clearly the topic of image generations. That it is a deterministics, and you have to explain the generative modeling framework, probabilistic generative model, samples of generative models by the use of Navy Bayes classification algorithm. And I would like to the participants for the making this event as a grand success. Once again, I thank one and all present here. Thank you so much, sir, for giving the nice information related to the autoencoders, and the participants also give the nice feedbacks about your event. It is a very useful session, so all are given the information regarding your event, sir. Thank you so much. Thank you. Thank you so much.
Dear participants, feedback link is posted in the chat box. Kindly fill the feedback link.